Today we discussed how to find sampling means confidence intervals with means. We've been working with proportions, and means are a little bit different. So we started with this example where we found the point estimate, and when we're talking about mean, our point estimate is our statistic, which would be our X bar, which is our sample mean, and then we identified the different ones. Now there are conditions to have to be able to use this, and the first condition is it has to be random, same as proportions, because we're using it as a generalized statement. So it does have to be random. The second condition is a large count or normal. So a lot of times when we're dealing with means, we have a very small count, and that's okay as long as it's a normal distribution for the population. So if we're pulling a sample randomly and we have only 10 people, that doesn't meet the large count of mean of having our sample be 30 or larger. But we could still use it if they tell us that it is normally distributed, or we know that the population itself is normally distributed. A lot of times you can think about the population, you can kind of plot it on a graph and see if there are any major outliers, and that's a way to help see as well. So that's the second condition, is large count or normal. Then we talked about how before in means we would find the standard deviation for the population by this formula here. But this time with a sample, we do not know the standard deviation of the population. If we did, we wouldn't have to estimate anything. We could just use z's, but we don't know it. So we have to use the sample standard deviation, which is abbreviated as SX, and we divide that by the square root of n. That gives us our standard error for our sample for the mean. So that new formula here is what we talked about here that you need to know for standard error. And so then we calculate our standard error was 14.8, which is what they gave us for our SX up in the problem, divided by a square root of 30, and we got 2.7. So that is our sample standard deviation. Then we went in to talk about when we did proportions, we use the Z critical values, but for these we have to use the T critical values, so it's T distribution. And the reason that is because we are estimating not only the average, but we're also estimating with the sample standard deviation instead of the true. So we're doing more estimating, more things, so it's getting further and further away from the possibility of correctness, precision. So we're having to use a different distribution, and that accounts for that issue. Now to do that, we talked about where they get T from, and it's just taking our sample mean minus the population mean, which of course we don't know, but this is how that works out, divided by our standard error. So that's kind of how T comes about. But we don't have to do all that. We're going to use the table. So to be able to use the table, we have to find the degrees of freedom. And degrees of freedom are just the number of our sample size minus 1. So in our case, we had 30 minus 1, so our degrees of freedom are 29. Then we move to our table, our T distribution, and we are looking for, as it said in the problem, a 95% confidence interval with a degree of freedom of 29. So when we go to our table, we use the T side, and if we look at the top, we have a confidence interval, 1-tail and 2-tail. We'll talk about the 1-tail, 2-tail later, but we're doing 95%. So we're looking for the 95%, and our degrees of freedom, because we calculated, are 29. So here's 29. So when we go over to where we meet here, 2.045 is what we will use for our T. Now, we'll just write it down for the moment there. And now we are going to calculate our margin error. So before in population or proportions, we used Z times the standard error. Well, this time we're using T times the standard error. So we've already talked about standard error before, and we're going to multiply it times T. So when we do that, we got 5.52 for our margin of error. Now, to find a 95% confidence interval, we are actually going to take our point estimate and add or subtract our margin of error. Well, before, when we did this with proportions, we used p hat, that was proportion, plus or minus the Z critical value, and then we used this formula p hat, square root all this good little jazz here, for our standard error for proportions. But for means, our point estimate is our X bar, and we plus or minus our T critical value, which we've already found above, and then our standard error. Well, we've already calculated this T times the standard error and got our margin of error. That's our 5.52. We did that number 7, and then we're going to add it to our point estimate, which is what we were given in our problem, 25.3, and also subtract it, and that gives us our intervals. Now, We know this is in minutes because we're talking about YouTube viewing. So when we write our statement and interpret it, we are 95% confident that the interval from our lower bounds or upper bounds we have in our units, minutes, captures a true mean statistic of the daily viewing time for YouTube. So I always put it in context. Now, we then went over some basic conditions. Both proportions and means have to be random and meet the 10% rule. And then the large or normal sample is the only difference. For proportions, we do the n times p hat, and then the n times 1 minus p hat, and these both have to be greater than 10. But for our mean, we have to either have the population distributed normally that they tell us or we know from data collection, or our sample size has to be greater than 30. Most of the time, you will see small sample sizes and assume that they're normal. Sometimes you can't, and you can't go further. Then we talked about critical values. Z are used for proportions. T's are used when we talk about means. And that's pretty simple to kind of keep it that way. There are times when you can use Z for means if you're given some other things so that you know you're not having to estimate more than one item. That's why we're using T, because we're having to estimate more than one thing. You do have to know how to find your degrees of freedom, which is n minus 1. If the degree of freedom is not listed on your chart, you can go one below it. So, for example, on your chart, if you were looking for 39 and it's not there, you can move to 35. Some charts stop different places, but I'm going to show you how to use the calculator. If you're not sure, and you can do a conservative estimate of 30, knowing that you have to have at least 30. So you could use the critical values for T of 30, or degrees of freedom. Then we talked about our formula one final time and put it in there all together, broke it down. Now, we talked about the cookies and how to find that and how to interpret like the meaning of that. And then we want to talk a little bit about your homework. So we did talk about how to put items in a calculator into our stat edit, enter our data, and then stat calculate in the number 1 vars, knowing that SX is your sample standard deviation, which you'll use in your formulas. If you look at like number 1, it says find the t-value such that the area to the right tail is 0.10 with a 25 degree of freedom. So when we look at the right tail here, we're talking about this little section here is 0.10. So we think about if this whole thing is 1 and we're taking away 1 minus 0.10, then we actually have from here is 90%. Okay, so you can kind of look here, and the 0.10, when you look at what's up here, we have 1 here, we have 1 here, and we're like, well, what's happening? Okay, so when we look down and we try to find a degree of freedom of 25, we go here, we would have either here or here. So let's see what makes sense. When we think about one tail area, it's saying to the right, on the right tail is that 0.10. So that means we are looking at this whole right section being 0.10. And so we're looking for something that goes all the way over this t value right here. And this can be a little bit confusing for people to see what is actually going on. So when we think about that, we were like, well, we want to think about the 90%, but we have to think about what's in that one tail. So I'm going to show you on a calculator how to do that and in Desmos. Second vars, you can go down to the inverse t, okay? And when you do that, you put the area that you're talking about. So this is 0.10, and then we do comma, and then we're going to do our degrees of freedom. So our degrees of freedom were 25. And we get a negative 3.16. When we do that, we're thinking about we have on the negative part, we are looking at to the right. Remember, these tables tell us to the left. So when we put that in, it's telling us this little chunk over here is 0.10. And that's why we got a negative. Well, we know we don't need a negative, so you can just ignore the negative. The other option is when you put it in, instead of putting in 0.10, put it in with the 0.90, and then comma with our degrees of freedom and enter. Now on your calculator, it may look a little bit different. Now this is the same thing that you would get on your table when you're looking. Now, I'm going to show you how to use Desmos as well. A couple ways to do this, and I wanted to show you with a picture. So if you put in the inverse CDF of the t distribution, our degrees of freedom were 25, and then we put in the 0.90 because I knew that to the right of what I'm doing is 10%. So where I'm looking for all the way to the left, which is what t-tables give us, is the 0.90. And so I got the 1.316, same thing that the calculator gave me. Now, if I want to check that and kind of see a visual of that, if I do t distribution and I do my degrees of freedom 25, and I put my max as my 1.316, I can see it's almost 90% rounded. That's why it's giving me that. But you can get a visual here of what's happening. So all the area that's shaded is the part that where it starts is the t value. And so to the right of that is that 0.10. Now, if I were to do number 2, of course, I'm dealing with the 0.05 to the side, so I'm actually dealing with 95% going to the left. So even though it says 0.5, we think, oh, we'll put 90, it's 95 different. It's pretty easy to see if you start thinking about it. Now, when we do something like number 3, it looks a little bit different. We can actually do the t distribution inverse, and we're going to do to the left, we're doing 1. So we have a freedom of 18, and then our 0.01 that's to the left, and now we're getting a negative 2.55. So if I then check on this one and do a negative 2.55 with my 18, I can see that it's roughly 0.01, which is what's to the left. And if I look at my shape, I can see really, really small that this is the area that is shaded. So I'm looking for the t value that starts where that shaded is, and then everything to the left is what it's going to give me. On one of the homework ones for the very last question, it asks you to do a 96% confidence interval, and on your table there is no 96% confidence interval. So we find our degrees of freedom, which is 9, and then we're going to use this concept to find it. So we're going to put in our degrees of freedom as 9, and then we are looking for a 96%. We're looking for 96%, and so either side of that is 2% each. They're split up in the tails. Well, we're looking for this t value that starts right here, and that goes all the way this way. So it is actually including 96 plus 2% more. So when we put it in, we actually put it in as degree of freedom of 9 and then 0.98, and it gives us a t value of 2.3984. Of course, I rounded, and then you would calculate from there.